introduction to the normal distribution. Righty, so this is following your notes booklet, so you can fill in the missing blanks as we go. So introduction to the normal distribution. So the normal distribution is the most important and most widely used distribution in statistics. It's sometimes called the bell curve. I'm not sure if you've heard about it if you've studied psychology or biology. It's also called the Gaussian curve, named after the mathematician Carl Friedrich Gauss, who appears in this picture up here. So look at the normal distribution below. This is an example of the normal distribution down here, and describe some of its features. So looking at the general shape of the curve, what do you think I'm kind of saying here? It's something, and the shape is generally something starting with SY. So it's kind of like a mirror image either side. So what word would you use? You probably guessed it's symmetrical. So the normal distribution, it's a symmetrical graph, meaning like if you can draw a line down the center and it's a mirror image either side. And the area underneath it is, so if you added up all these areas, the area underneath it is equal to 100%. So this area underneath the graph, we generally say it's equal to 100%, but more commonly, rather than say 100%, we'll write it as a decimal. 100% as a decimal is the number 1. So by definition, the normal distribution, it's this bell-shaped curve. It's symmetrical around the mean. The mean is this center point here. And the area underneath the normal distribution is always defined as being equal to the number 1, meaning 100%. The highest point corresponds, so the highest point is just here, corresponds with which symbol? So that little symbol here, and that's got a special name. It's mu. So this little symbol is mu. If you're not sure how to write it, the way I tend to write it is I tend to do the little line first, and then next to it, like, or attached to it, you just draw the number, the letter U. So that's how you do a mu. So when it comes to the normal distribution, we use the symbol mu to represent the mean. Remember, in stats, we generally kind of use this symbol to represent the mean. But when we're doing the normal distribution topic, we use the symbol mu to represent the mean. So the highest point here of the bell curve of this normal distribution corresponds with the symbol mu, which is the mean, on the x-axis. So the x-axis, of course, is the horizontal axis. And notice that either side of here, we're kind of trying to define what overall the area underneath the curve is 100% or 1. So the area either side, like if you went the mean plus 1 standard deviation, then that area is defined as being exactly 34.13%. And the mean minus 1 standard deviation is defined as being 34.13% too. So if you were to say these two areas added together, these two areas would be equal to 34.13 plus 34.13, or double 34.13. That gives you 68.26% of the data. So it's saying 68.26% of the data falls between the mean minus 1 standard deviation. Remember, this funny symbol here is a symbol for the standard deviation, that little symbol there. So we're saying that 64, by definition for the normal distribution, 64.26% falls between the mean minus 1 standard deviation and the mean plus 1 standard deviation. So this area here is meant to represent 68.26% of the data. So it falls beneath the mean minus 1 standard deviation and the mean plus 1 standard deviation. So what we're trying to fill in here is kind of like what we did. This is a mean minus 1 standard deviation. The mean plus 1 standard deviation, to be written in symbols, would be this here, mu plus sigma. So that first symbol is mu, represents the mean. That funny symbol there is sigma, represents the standard deviation. And now they're asking what percent of the data falls between the mean minus 2 standard deviations and the mean plus 2 standard deviations. So they want to know what percent of the data falls between here and here. So we just need you to add up these four percentages here. So if you add up that plus that plus that plus that, or another way of thinking of it, because it's symmetrical, it's this plus this, and then doubled, because that plus that is the same as that plus that. So I just added up those two and I doubled it. which would give me this whole area under here. When you double these, double the sum of that, if you plug it into your calculator, you'll get 95.44. These four percentages added together give you 95.44% of the data. Falls between the mean -2 standard deviations and the mean +2 standard deviations, which is written in symbols there. That's another special thing about the normal distribution. And lastly of all, what percent of the data falls between the mean -3 standard deviations and the mean +3 standard deviations? So they want to know what percent of the data falls between here and here. So they just want you to add up that, plus that, plus that, plus that, plus that, plus that, which you could also think of it as being this, plus this, and then doubled, because that plus that is the same as that plus that plus that. So adding up those 6, well, I added up the 3 and then I just doubled it. So if you plug that into a calculator, add up all those probabilities or percentages, you get 99.74% of the data falls between the mean -3 standard deviations and the mean +3 standard deviations. So that's pretty close to 100%, isn't it? So notice looking up here, so pretty much it does look like that, doesn't it? It looks like almost 100% of the area under the curve falls between this point and this point. Outside is just a tiny amount. This side there's a tiny amount of the data, 0.13%, and outside here 0.13%. So it's kind of like saying, like, you know, how people tend to say exam results. Majority of students they predict will fall in the middle somewhere. Only a small percentage of students score really high scores, only a small percent of students score really low scores. That's generally how exams are distributed. Okay, so if that's confusing you, that's fine. Let's just move on. So you can go and watch these 3 videos in your own time if you want, but if you do them, you'll probably find many types of phenomena in the real world fit this type of distribution. Watch these videos and list some of the examples given. So heights of students, for example, cockle shell lengths, like a lot of things in biology, follow these normal distributions, the size of bunnies, the weights of bunnies, etc. So generally saying the majority of people are in the middle, or animals, and only a small amount are really short, for example, only a small amount are really tall. So there's a lot of phenomena in biology and sort of society in general that kind of follow these kind of normal distributions. So now what you might want to do is you might want to pause this video, because if you haven't filled in this page here, I want you to go back and on Firefly, watch the first video that is posted on there. That's this video, and then you'll find that you can answer this particular page. So it asks you to fill in, if you have paused and you've come back now and you want to check your answers, so you're asked to fill in the x-axis, to label it, to shade certain areas, and so on. Calculate what the standard deviation must be. So the standard deviation, because that's the mean in the middle, mu, standard deviation plus 1 is 115, standard deviation minus 1 is 85. So one standard deviation must be equal to the difference here, which is 15. What real life situation is being modelled in this video? They're saying that IQ scores are modelled by this, saying that majority of people, like 68.26%, fall between the mean minus 1, the mean plus 1 standard deviation. Only a small percent of people in general score low IQ, a small percent of people in general score very high IQ. Majority of people are in the middle. That's what this normal distribution generally tells you. So that's the answers to that video, but hopefully you've paused and gone and watched it properly, because it's a bit more interesting than me just summarising it. So moving on, what kind of questions can you answer now? So let's see a little example here. So we're saying the chest measurements of 18-year-old male footballers are normally distributed, meaning they follow this bell-shaped curve. Whenever you see questions saying they're normally distributed, it's a normal distribution question, with a mean of 95 centimetres and a standard deviation of 8. So what's really important is mean of 95 centimetres. I've kind of put a graph here to help you, meaning what number should go down here? This should be the mean, mu. So see, 95 centimetres should be here. There's a standard deviation of 8. So the mean plus 1 standard deviation, think of what's 95 plus 8. 95 plus 8, think about it. Yep, it's 103. Then the mean plus minus 1 standard deviation must be 95 minus 8. What's 95 minus 8? Yes, you're right. It's 87. Try to fill in also what's the mean plus 2 standard deviations. So 103 plus another standard deviation would give you up to 111. 103 plus 8. The mean minus 2 standard deviations would be 95 minus 8 minus 8. Think about what that would be, or use your calculator. You should get 79. So that kind of helps you kind of just planning it out on a graph like this. These percentages still apply from the previous pages. So 34.13% here, 34.13% here, 13.59% here, 13.59% of the data is here. So you're asked to find the percentage of footballers with chest measurements between 87 and 103. So this graph is definitely going to help you because they want to find percentages by adding up these percentages under the curve. So 87 and 103, have a look. 87 is here, 103 is here. So what percentage fall between this point here and this point? Basically, what area under the graph falls between here and here? And so you can use these general numbers. 34.13 is this area here, plus 34.13, which is that area there. So I've given myself a little clue. I've written within plus or minus 1 standard deviation. So mean minus 1, mean plus 1. So as you can guess, you can write 34.13 plus 34.13, or you could do what I've done, which is double 34.13. I mean, double that, you get 68.26%. So 68.26% of footballers have chest measurements between 87 and 103 centimeters. That's how you apply it to real life. Question II. What percentage of footballers have chest measurements between 103 and 111? So 103 is here, 111 is here. So what percentage is under here according to the normal distribution? That's 13.59%. If you're wondering where these percents come from, they come from this page earlier on. This page here. See, they're just the same numbers as what we've got here. So the percent that have chest measurements between 103 and 111, it's just 13.59. So that's why there's nothing to calculate there. It's just one particular area there. And further down, find the probability that the chest measurement of a randomly chosen footballer, so same question as above, is between 87 and 111 centimeters. And I've said your diagram above might help with this. So let's have a look. 87, where's that? Here. 111, where's that? Here. So you've got 3 areas to add up. So you've got 34.13 plus 34.13 plus 13.59 is between 87 and 111. So you might want to show some working out for that. Different ways. You can just show them all added up, or you can do like what I did, 2 times 34.13 plus 13.59, or you could have just separately added the 3 numbers. If you plug that into a calculator, you should get 81.85%. Exactly. So 81.85% of footballers have chest measurements between 87 and 111 centimeters. So these are just showing you examples of how you can apply this to the real world. Now let's move on to some more examples. To try. Explain why it's likely that the distributions of the following variables will be normal. So the volume of soft drinks in cans, or the diameters of bolts after manufacture. So try to think, why do the volume of soft drinks in cans follow this curve? Why do the diameter of bolts immediately after manufacture follow this general shape? So there's different things you can say for this. So what I've sort of said is, I've said the manufacturer will make sure the machinery delivers as close to the required volume or diameter, depending on question A or B that you're talking about, the mean, as possible. So the manufacturer will make sure that the machinery delivers as close to the required volume, which is the mean, as possible. However, equipment is not always perfect. However, due to some imperfections in the machinery, so not everything's perfect, or the processes in the factory, some items will vary a little from the mean. So you might get a few bolts that are a little bit smaller in diameter, a few bolts that are a tiny bit larger in diameter than the mean. Same with the volume of soft drinks in cans. It's pretty much always going to be very, very close to what it should be, but there might be slight deviations like +1 millimeter or +0.3 of a millimeter. So that's why generally the majority will be in the middle, around the mean, but there will be some cans that have tiny amounts that have less than the mean, or some cans, a few cans that have a lot more than the mean. So that's one way you could answer it. State the probability that a randomly selected normally distributed value lies between the standard deviation below the mean, so one standard deviation below the mean, and one standard deviation above the mean. So to do that, look back at your general question back here, your general one. So one standard deviation below the mean is here, one standard deviation above the mean is here. So what percentage is that when you add it together? You probably won't remember already. So it would be double 34.13. Then you would work that out. It is 68.26% of the data lies one standard deviation below the mean and one standard deviation above the mean. State the probability that a randomly selected normally distributed value lies between the mean and a value 2 standard deviations above the mean. So what do we mean by that? The mean and 2 standard deviations above the mean. So the mean and 2 standard deviations above the mean is here. So they want to know what area is represented by that. Between the mean and 2 standard deviations above the mean, it'll be 34.13 plus 13.59. So try to think how you would show that working out. So I've crossed something out there. 34.13 plus 13.59. Add it together in your calculator. You get 47.72% exactly. So it's all seeming reasonably logical so far, but let's try to apply it to a few more questions. It's another real life problem. The mean height of players in a basketball competition is 184 centimeters. So to remind myself of the symbol of the mean, I've just drawn that funny symbol mu there. That's the symbol we use for the mean. So the mean height is 184 centimeters. If the standard deviation is 5 centimeters, so I've drawn sigma there to remind me that it's equal to 5. What percentage of them are likely to be taller than 189 centimeters? So it might help to kind of do a rough sketch of the normal distribution. So I've kind of done the very first normal distribution. I've just drawn the normal curve. The mean goes down the center. So the mean is 184. And then the mean plus 1 standard deviation would be 184 plus 5. So mean plus 1 standard deviation is 189. Plus another 5, you'll get up to the mean plus 2 standard deviations. So that's 194. The mean plus 3 standard deviations is 199. So notice I just keep adding 5 as I go. Then to go the mean minus 1 standard deviation, I minus 5. Then minus 5 to get to the mean minus 2 standard deviations. Minus 5 to get to the mean minus 3 standard deviations. So I've just drawn the normal distribution in there to help me. So what percentage of them are likely to be taller than 189? So see 189's here. So we've got to add that percentage plus that percentage plus that percentage. That's one way of doing it. Oh, hang on, let's see, taller than 189. I think I might have done something wrong here. Let's just see. So I'll just fill that in. Oops. Okay, so I've said 13.59%, but 13.59% is actually just that percentage there. So I've actually made a little boo-boo there. Because taller than that, it should be that percent plus that percent plus that percent. So looking back to here, it should be that percent plus that percent plus that percent. So what's 13.59 plus 2.15 plus 0.13? You can plot that into your calculator, which I might do right now too. So it might just take me a second or two to do that. Okay, just while I get my calculator up. So I'm going to type in 13.59 plus 2.15 plus 0.13, and I've got 15.87. So let's go back and fix that up. Where are we? No, so we're down here. Hang on, I'm on the wrong page, am I? Oops. Here we go. So instead of 13.59, I should have 15 point, what was it again? 15.87. So taller than 89 is that area plus that area plus that area. That's why we had to add the 3 up, and you can show some working out in there as well if you like. Taller than 179 centimeters, so taller than 179 centimeters would be that. So 34.13 plus 34.13 plus this one 2.15 plus 0.13, sorry, and 13.59 plus 2.15 plus 0.13. That's what this is here. And then when you add all that up together, you should get 84.1%. Between 174 and 199, 174 is here, 199 is up here. So you've got to add these probabilities. So you've got 13.59. So basically, I just did 174. So I did 34.13 plus 34.13 by doubling it, plus 13.59. Plus I need to add these ones as well, don't I? So 174, so 13.59, 34.13 plus 34.13, plus I also need to add another 13.59, and so on. So I've just gone and fixed that up. So now you can see I've got 2 times 34.13 plus 13.59 plus 13.59 plus the 2.15, because that's between 174 and 199. And you should get 97.59% for that one. Over 199 centimeters tall just means this little area out here, which when you look back on your original normal distribution, that is 0.13%, is that little tiny bit outside. Here's another example here. The mean average rainfall of Claudona for August is 48 millimeters. So 48, so if you draw your normal distribution, 48 is the mean. So the mean is 48, mu is 48 millimeters with a standard deviation of 6 millimeters. So sigma is 6 millimeters. Over a 20-year period, how many times would you expect there to be less than 42 millimeters of rain during August in Claudona? So you draw your normal distribution, you tend to mark in where the mean is next. So the mean's 48, it runs through the center. So 42 must be somewhere to the left because it goes from smallest to biggest along the x-axis. So 42 is less than 48, so it's got to be off to the left somewhere. And it makes sense that the difference, it's basically the mean minus a standard deviation, isn't it? So the mean minus 1 standard deviation, the mean minus 6, is equal to 42. So they want to know how many times we expect it to be less than 42 millimeters. So they want to know what that area there is. So that area there, when you think of it, it's going to be like this. It's going to be that area, 13.59 plus 2.15 plus 0.13. So we can show some working out for that. Or another quick way to do it is when you think of it, the mean splits it into 50% and 50% because the mean splits it in half, and overall there's 100% area underneath. So the area to the left of the mean must be 50%. So, and that area here is 34.13. That's what this area here is. So you could have added these up separately, like I just said, or you could just do 50% minus that area there. It's a bit shorter. gives you 15.87%. And I changed that into a probability. Into a decimal. 15.85% as a decimal, just divide by 100, is 0.1587. And so over a 20-year period, how many times would you expect there to be less than that in Caledonia? So in 20 years, it would be 20 years times a probability of 0.1587 per year. So it would give you 3.174 times, which if you were to round that would be roughly 3 times. So that's meant to be a 3 there. So equals roughly 3 times. Over 20 years, we would expect there to be less than 42 millimeters of rain in Caledonia. So we took the probability, which is 0.1587, and times it by 20 to work out how many times. Let's keep moving on to do some more little practical examples. The weight of babies born at Prince Louis Maternity Hospital last year averaged 3.0 kilograms. So we know what the mean is, so that's mu, that little symbol there. So our mean is 3.0 kilograms with a standard deviation of 200 grams. So that's our standard deviation there. If there were 545 babies born at hospital last year, estimate the number that weighed less than 3.2 kilograms. So let's draw our little standard normal distribution. So you do your bell curve, you do your x-axis. First thing to do is split it in half and mark in the mean. So the mean was 3, so split it in half, mark in the mean as being 3. So 3 kilograms, the standard deviation is 200 grams, which when you think of that, 200 grams, because you've got to be kind of consistent with your units, 200 grams in kilograms, there's 1,000 grams in a kilogram. So 200 divided by 1,000 would give you 0.2 kilograms. So that might be worth doing. Convert your standard deviation into kilograms first, so you've got consistent units. And therefore, so in our picture we've got our mean of 3. So the mean plus 1 standard deviation would give you the 3.2 kilograms. So they want to know, estimate the number that weighed less than 3.2. So less than 3, because the standard deviation, the mean splits it into 50% and 50%. So less than 3 has got to be 50%, plus this little area here, which is 34.13%. So if you add that together, 50% plus 34.13%, add it together in your calculator, you'll get 84.13%. As a decimal though, when you're trying to work out how many you get, it's not asking for a percentage, it's asking how many babies. So the probability, when you convert the percentage into a probability, you just divide it by 100. 0.8413. So that's a probability that the baby was less than 3.2 kilograms. So if there were 504 babies born in total, how many would we expect to be less? You just take 545 times the probability, times 0.8453. So we expect 458.15 babies to weigh less than 3.2 kilograms, but we can round that to roughly 459 babies, because you can't get 0.5 for baby. Estimate how many babies weighed between 2.8 and 3.4 kilograms. So again, you've got your mean through the center. 2.8 is just 1 standard deviation below the mean, and 3.4 is 2 standard deviations above the mean. So you're going to add this area here, 34.13, plus this area here, 34.13, plus this area here, 13.59. So you might want to show a little bit of working out for that. So 34.13 plus 34.13 plus 13.59 gives you 81.85%, which divided by 100 to turn into a decimal is 0.8185. It's a probability that they weighed between 2.8 and 3.4. So how many in babies? You take how many babies there were in total and times it by the probability that's between 2.8 and 3.4. So you get 545 times the probability that it weighs between these two weights. You get 446 babies is how many we expect to weigh between 2.8 and 3.4 kilograms. Another practical example, the heights of male students in a university is normally distributed with a mean of 170. So our mean is 170, you might want to write that out, mu equals 170, and a standard deviation of 8. So I'd write out the sigma equals 8. It's a good thing to do. Find the percentage of male students whose height is between 162 and 170%. And I've kind of put this graph down here to kind of help you get started. So you probably want to mark in the mean through the center. The mean is 170, mark it in. So the mean plus 1 standard deviation will be 170 plus 8, which is 178, plus another standard deviation to get up here, which would give you 185. The mean minus a standard deviation is 170 minus 8, which is 162, minus another standard deviation gets you to 154, and so on. So between 162 and 170, so between 162 is here and 170 is here, so it's just that amount there. So find the percentage. They want the percentage, so it's just 34.13. I rounded it to 3 sig figs, but you can also say 34.13 is okay too, because it's an exact answer. Between 170 and 186, so 170 is the middle, and 186 is 2 standard deviations above the mean. So you've got to add 34.13, this area, plus 13.59. So when you do that, you might definitely want to show you're working out so you can get some method marks in case you make a boo-boo. I rounded to 3 sig figs, 47.7%. You could also just write it as an exact answer with 2 decimal places if you like. And that's the answer to A. So find the probability as a decimal. I'm going to say let's find the probability as a decimal rather than a percent, that a randomly chosen student from this group has a height between 178 and 186. So 178 is here, 186 is here. So 13.59 is the percentage, so 13.59% or 13.6%. To turn it into a probability, you just divide the percent by 100. So divide by 100 means move the decimal point 2 spaces to the left, 0.136%. You can also write 0.1359% because that's an exact answer. Less than 162, meaning this percentage here plus this percentage here plus this percentage here. Or you could think of it even easier. Remember, like the mean splits it in half, 50%, 50%. So less than 162 would be 50%, which is this whole area here, minus that area there. So that's sometimes a bit easier. So 50 minus 34.13 tells you what's remaining over here. 15.87 divided by 100, you get 0.159 or 0.1587%. Less than 154, so we've got minus 1 standard deviation, minus 1 standard deviation. So we've got to add these last 2 areas together. So remember, it was 2.15% and 0.13%, wasn't it? Less than 154. So, or the other thing, yeah, as I've done here, you could do just 50%, which is the whole area, minus 34.13 minus 13.59. I also did that. That gives you 2.28%. Divide by 100 to turn into a probability, and you will get 0.0228%. Greater than 162 centimeters. Where's 162 centimeters? It's here. So it's basically 50% is that area here, plus 34.13. So greater than 162, that's a quick way to do it. 50 plus 34, 50 is that half here, plus that little area there, 34.13%, which gives you 0.841, or 84.13%, which gives you, divide by 100, gives you 0.841 or 0.8413 as an exact answer. And so on. So now let's just do a little summary. So what kind of fancy symbols have you learnt? What's the symbol for the mean when we do the normal distribution? The symbol for the mean is that funny symbol there, mu. Just a reminder how to do it. I tend to draw the little tail first at the front, and then the letter U. Okay, the standard deviation, the symbol for that is sigma, that little symbol there. The continuous variable, we tend to say, is x, continuous variable x. bit that, notice that's capital X. The variance, which is just a standard deviation squared, So you're going to start to see some questions written using these funny symbols. So now, instead of asking you to find the probability using regular language, a question might state this: big X, swervy line, n, brackets, mu, comma, sigma squared, close brackets. This literally translates to, the purple part is the continuous variable, obviously X, capital X. The green part means is distributed, so that literally means is distributed. The big N in red means normally. So the continuous variable X is distributed normally with a mean of mu, of course, and a standard deviation of sigma. So ignore the squared part, it's just saying that the standard deviation is sigma. So you're going to start to see some questions where it's kind of written like this. This means the continuous variable X is distributed normally with a mean of mu and a standard deviation of sigma. So let's see some examples over here. So try to turn these symbols into words, like similarly to what was done on the previous page. So remember, it begins with the continuous variable, and don't forget that it's big X. What does that curvy line mean? Try to remember. It means is distributed normally. I said is normally distributed means the same thing as distributed normally, with a mean of, in this case, they've actually told you what the mean is. So with a mean of 170 and a standard deviation of, try to think, is the standard deviation 16 or is it 4? The standard deviation is 4, just that number there, so ignore the squared. So that means the continuous variable X is distributed normally with a mean of 170 and a standard deviation of 4. So it's another way of giving you a question where they just don't say the word standard deviation and mean. They just put it in symbols instead. Same thing, what does this one mean? Means the continuous variable, so don't forget to write this in, the continuous variable X is distributed normally, or is normally distributed, same thing, is distributed normally with a mean of, have a look, it's 56.8. So the first number, remember, is always the mean. The second number is the standard deviation, and ignore the squared. And a standard deviation of 2.1 is what that translates to. And so let's see some examples like that. So imagine they gave you the question using symbols instead of putting it into real life sentences. So they're saying, suppose the continuous variable X is normally distributed with a mean of 16 and a standard deviation of 3. So you could go straight to saying the mean is 16, U is 16, the standard deviation is 3 is a good thing to write out. So find P. So they want you to find the probability that the value is between 13 and 16. So I've drawn this normal distribution down here to help you. So you would do a little sketch of the normal distribution. I would put a line down the center, mark in that the mean is 16. Maybe also mark in the next standard deviation, one standard deviation up, which is 16 plus 3, and one standard deviation down, which is 16 minus 3, plus maybe a second one and a third one if you want. So you could have this 2 standard deviations down is 10, 3 standard deviations down is 3, and so on. And you've got these relative percentages here. So between 13 and 16, what is that little area there? Remember, it's 34.13. So they want it as a probability though, so 34.13% divided by 100 is about 0.341, or 0.3413 is also okay. So now they want to know, find the probability that X is less than or equal to 13. So less than or equal to 13 means this whole area here. So remember, the shortcut is to go 50% minus 34.13. And then I would suggest, so then work out what that is as a percent, and then divide it by 100 to turn into a probability. Find the probability that X is greater than 22. So greater than 22 is up here. So in a way you could also think of it as it's 50% minus that probability percent and minus that percent. So 50 minus 34.13 minus 13.59. You could have also said it's 2.15 plus 0.13. That's another way of doing it. You get 2.28%, and to turn into a probability, you divide by 100, which is 0.0228 as a probability. Here's another example. We'll try to make it a bit more real life again. So when a specific variety of radish is grown without fertilizer, the weights of the radishes produced are normally distributed with a mean of 40 grams, so a mean of 40 grams, and a standard deviation of 10 grams. When the same variety of radish is grown in the same way, but with fertilizer added this time, the weights of the radishes produced are still normally distributed, but the mean in this case, when there's fertilizer added, is 140 because it makes them grow bigger, and the standard deviation of 40 grams. So wider distribution, like more variability. Determine the proportion of radishes grown without fertilizer, so without fertilizer, with weights less than 50 grams. So do a quick normal distribution sketch, a very rough one. The mean in the first case, so without fertilizer, the mean is 40. So marking the mean is 40. Standard deviation is 10. So the mean plus 1 standard deviation is 50. Mean plus 2 standard deviations is 60. Mean minus 1 standard deviation is 30. The mean minus 2 standard deviations is 20, and so on. You could also mark in the 10 and the 70 if you want. So with that fertilizer, less than 50 grams will be 50% is below the mean, plus this percentage here, 34.13. So 50 plus 34.13, they want to know the proportion. 84.13% is the proportion, or as a decimal, oh, I said, actually no, I just put it in as a percentage, but I just rounded to 3 sig figs. You could have also said 0.841 is also okay, but I'd put them in as percentages because they didn't say probability or percentage, so either one's okay. So determine the proportion of radishes grown with fertilizer, so with this mean and this standard deviation this time, less than 60 grams. So let's see, less than 60 grams, I might need to scroll down because I've got my answers further down here. So this is for the one without fertilizer. This is, we can use for the one with fertilizer if you like. So with fertilizer, the mean was 140. And the standard deviation is 40. So the mean plus 1 standard deviation is 180. Mean plus 2 standard deviations is 220 because we're going up by 40. Mean minus 1 standard deviation is 100. Mean minus 2 standard deviations is 60, and so on. Then 20 down here. Okay, so you can fill those in. So which one? So with fertilizer, with weights less than 60 grams, so I is for with and without fertilizer with weights between 20 and 60 grams. So let's see, I can fill those ones in for you just so you can see what we're doing. So let's see, this is it, C, I. So you can see I kind of worked them out in the reverse order. I kind of did the first one. So with fertilizer, between 20 and 60. So between 20 and 60 is just this tiny amount here. So between 20 and 60 with fertilizer is 2.15%. Another way you could do it is, yeah, you could work out like that 50% and so on. Well, actually, it's just 2.15%. It's just that little bit there between 20 and 60. Without fertilizer, between 20 and 60, though, is here. Between 20 and 60, you've got to add up all those probabilities. So you've got to add 34.13, 34.13, 13.59, and 13.59, which I did here. And when you add those up, so without fertilizer, it's 95.4%. And D, so we're saying with and without fertilizer, with weights greater than 60 grams. So let's just check which order I've done it in. Okay, so weights, let's see, greater than 60 grams. So greater than 60 grams out here, you could think of it as just being 50% minus 34.13 minus 13.59 means greater than 16, and so on, which is basically that one there, 2.28%. And for this one with fertilizer, it was for greater than 60. So greater than 60 is that big amount up here. You can think of that almost as being 100% minus that. So it could be 100% minus 2.15 minus 0.13, or you could have just done 13.59 plus 34.13 plus 34.13 plus 13.59. Or you could have just done even easier, 50% is that whole bit here, plus 34.13 plus 13.59. And you can see that's what I did there, 97.7%. Okay. So more examples, I think this is the last one. A bottle filling machine fills an average of 20,000 bottles a day. So average meaning that the mean, mu, is 20,000. So make sure to write that down, with a standard deviation of 2,000. So they're big numbers, but it's still possible to do the question, no problem. So sigma equals 2,000. Assuming that production is normally distributed and the year comprises 260 working days, calculate the expected number of working days on which under 18,000 bottles are filled. So remember that the mean is 20,000. So 20,000 represents this point here, and 18,000 is the mean minus 1 standard deviation. So it kind of means if 20,000's here, 18,000's just got to be 1 standard deviation below. So probability will be, or the percentage first of all, will be 50% minus 34.13, which gives you 15.87% is that shaded area there. It's always good to do a sketch first. And then, because turn that into a probability by dividing by 100, 0.1587, take the probability times by the total number of days to get how many days we expect. We expect that for 41 days, there would be under 18,000 bottles filled. And B, calculate the approximate number of working days in which over 16,000 bottles are filled. So again, here's our normal distribution, do a sketch of it. You might want to mark in your mean, of course, to start with. Then the mean plus a standard deviation is 22,000. The mean plus another is 24,000. Mean plus 3 standard deviations is 26,000. And going backwards, we've got 20,000 down to 18,000 because we're minusing 2,000 each time. 16,000, 14,000. So over 16,000 bottles are filled means this whole area here. So this whole area here, a quick way to do it is that's 50% here, plus 34.13 plus 13.59. Which, I can do down here. 50 plus 34.13 plus 13.59 equals 97.72%. And then turn that into a probability by dividing by 100, 0.9772, and there's 260 working days. So times by 260, you get 254 days in which we expect over 16,000 bottles are filled. And then C, between 18,000 here and 24,000 bottles to be filled. So the percentage is going to be 34.13 plus 34.13 plus 13.59. So work that out first. And then that will give you 81.85%. Turn it into a probability by dividing by 100 and times by 260 days, which is how many days you've got in total. So we expect 213 days where there would be between 18,000 and 24,000 bottles filled. And so remember, doing these sketches is really important because it helps you kind of get a bit of an idea of where to begin. And that's kind of the end. Like if you want to check any other answers, like these, a lot of these questions kind of came from the textbook, and there's some little answers there. So sometimes the answers are exact answers, sometimes they're round to 3 sig figs, but exact answers are fine. It's only when you're rounding an answer that you're required to round it to 3 sig figs. And if it's a percentage they want, don't forget to write the percentage symbol. If it's a number of days, don't forget to write days, and so on. If it's a probability, don't forget to write it as a decimal. So basically divide the percentage by 100 to turn it into a decimal. and so on. And that's the end of lesson 1.